All right, hello, welcome. In this video, I'm going to be recapping Calculus BC Unit 6. And this is the unit where we're first learning how to integrate. We are finding the area under a curve and what else? Really just solving problems related to area under the graph of a function. So, I'm going to just give you a quick topic list and then I'll dive in deeper into each of the lessons. So in 6.1, that was the idea of the Riemann sum and kind of the definition of the definite integral that, you know, the true area under the curve is the limit of the Riemann sum, and that we can find some of these definite integrals by using geometry formulas. Okay. So I'm going to just write all those things down there. Yeah, so that's just the fact that this notation means the area underneath the graph of f between x equals a and x equals b really means the net signed area, because, you know, we decided that if the function went negative, that would count negatively towards the area. And then especially, and we saw more evidence of that when we learned the fundamental theorem, but we're not quite there yet. Left, right, midpoint, and trapezoidal sums, those are sums we need to be able to take to approximate this area. And then we need to be able to find the exact value of some areas that are composed of, like, you know, triangles, rectangles, squares, trapezoids, parts of circles, things that we know how to compute the area of from our geometry class a few years ago. Okay. Then in 6.2, that was the fundamental theorem of calculus. Okay, and that's how we take an integral algebraically. Okay, so that was really the theorem, was that if we wanted to evaluate the integral from a to b of some function, we needed to find an antiderivative for it and evaluate it and find the net change in that antiderivative between x equals a and x equals b. So that means that that's equal to f of b minus f of a. Okay. And that was, you know, lots of practice there. And that's how we take an integral. And we're going to just, you know, you're getting better at this over time. You have gotten much better at it since we started, but you still have a long way to go. And we're going to continue to get better over the course of the rest of this semester and the entirety of next semester. So, you know, practice makes perfect with this one. But that was pretty much all we learned. There was how to take an integral. 6.3, okay, we need to be aware of U-substitution. So change of variables, U-substitution, U-du integration is, I think, what I'm going to call that. And the key here was you had to recognize the pattern, okay? And remember that U-du is how we deal with some chain rule issues. And and this kind of, I feel like this can break down into two scenarios. We could either have something like kind of a minor chain rule inconvenience, like the integral from a to b of, you know, f prime of 6x dx or something, you know, some number of x's. I don't think that's worth doing a use of. Just trying to find an antiderivative for f prime of 6x. Well, a good first guess would be f of 6x, but then you remember that there's going to be some chain rule difficulties there, and you're going to have to divide by 6. And then we could, you know, evaluate that between, I was going to emphasize that's x equals a and x equals b. Okay, and we know how to do that. Okay. The one that's going to require U-substitution is where we have the integral from x equals a to x equals b of f prime of g of x times g prime of x, and I got room here, dx. Okay. What we do is we let u equal g of x, the inside. So really the key aspect of this that you have to be able to recognize is that you've got something in your integrand, and its derivative is appearing elsewhere with multiplication. Okay. That is the defining aspect of U-substitution. So u is going to be the thing that I could take the derivative of and see it elsewhere. U is equal to g of x. So then du dx is equal to g prime of x. And then we multiply both sides by dx, and I get du is g prime of x dx. And it's like, oh, look, hey, I've got g prime of x dx right there, and I'm going to make that into du. But if it's a definite integral, I need to make sure I convert my bounds as well, so that I don't have to go back into x's at the end, because that's just way too much work. So, you know, in this, I'm just working a very generalized example, so I won't really have any, I won't be able to say anything besides a and b go to g of a and g of b. But usually you can, you know, if it's u equals x squared, then u be a squared, b squared. But, you know, in this case, we don't know what g of x is. So then I'll say this integral now becomes the integral from u equals g of a to u equals g of b, which are two other numbers, of f prime of, well, u equals g of x, so that's f prime of u du. Okay. Take that antiderivative, that's going to be f of u. And then you would plug in this u value and that u value, and you would subtract them. Okay, and that's change of variables. But this is just the setup. I will work one of these you know, momentarily. Okay. Then in the fourth lesson, more motion problems, and we've done this already a couple of times this year. So this was where we learned how to get an ending position from a starting position and a given velocity. And you'll see I'll talk about this more in the Unit 7 recap video as well. But we'll say maybe, you know, if x is position and v is velocity and v is given, we've got the position at time b equals the position at time a plus the integral from a to b of the derivative of x, which is velocity. That's just a restatement of the fundamental theorem. But what we can also say is that since the integral from a to b of velocity is x of b minus x of a definite integral on velocity gives you a change in position, which we sometimes call displacement. Okay. Then we also need to know the formula for total distance traveled. Okay, total distance traveled, that doesn't care if we're going backwards or forwards. We don't want to be adding up negative velocities to make it seem like we're going less distance. Okay, everything needs to be positive, so that's why we're going to, for total distance, we're going to integrate between two time values that are going to be given to you as part of the question. We're going to integrate the absolute value of velocity. And again, this absolute value of a function, as far as anti-differentiating it, it's pretty hopeless. So what you're more likely to do is have this on a calculator, you know, have this in a calculator section of the multiple choice or or in the free response, right? Or in the free response, if you weren't allowed a calculator, it would say set up an integral, but don't evaluate it to represent the total distance, and that's all you would do. Okay, so let's dive in. All right, so for 6.1, let's just make a little x and f of x table. And what am I saying here? X and f of x. Oh, so yeah. 0, let's say 2 and 5. Okay, this is, you're not ever going to have one with just 3 x values. It would be at least 4, maybe 5. But, you know, for the sake of, I don't know, 10, 8, 4, something like that. Okay, and then suppose that we know that f prime is strictly negative. And I don't know about f double prime because these aren't evenly spaced. I'm not even going to go in there. I'm not going to ask you whether the trapezoidal sum for this particular example is an overestimate or an underestimate, but know that it's something I could ask you. Okay, so let's do some Riemann sums. Okay, left Riemann sum for the integral from 0 to 5 of f of x dx. That's going to be approximately equal to, well, the height of the rectangle I get from the left edge of the subinterval, and that would be 10, multiplied by the width in that subinterval is 2, plus height is going to be given by the left edge of that subinterval, that's 8, times the width here is 3. Okay? A right Riemann sum would be the integral from 0 to 5 of f of x dx is approximately equal to, well, I would use the right endpoint, so I would use 8 and 4. Okay, the widths are still 2 and 3, though. Since this is a decreasing function, a left Riemann sum will be an overestimate, and a right Riemann sum will be an underestimate, based on the decreasing nature of f, or the negative nature of f prime. All right, this table is not set up to do a midpoint Riemann sum. Okay, it would be if I had put in 1, and maybe that would be, I don't know, 9.5, and what would be halfway between 2 and 5, 3.5, I think, yeah. So if we had 3.5, then we could do the midpoint Riemann sum, and with still the intervals, subintervals 0 to 2 and 2 to 5. I'm probably not going to do that though, because that's not something that's going to be on the test, and 5 or something. Who knows? I don't think it's going to be necessary. So, but that would be, you would need these spots in the midpoint of your subinterval, and we don't have that. So, just ignore that. Okay, trapezoidal sum would be where we're going to average the heights and multiply by the width. So I'm going to average 10 and 8 and multiply by the width, and that would be 2. Then I'm going to average 8 and 4 and multiply by the width, which is looking like 3. Okay? So that's how we're taking Riemann sums. You need to be able to know whether the Riemann sum is an overestimate or an underestimate. Okay? For left and right Riemann sums, that quality depends on increasing, decreasing, or the sign of the first derivative of the thing you're integrating. For a trapezoidal sum, it depends on the curvature, or the second derivative of the thing that you're integrating on. Okay, but I think that's all I'm going to say about Riemann sums. Yeah, let me move up and talk about geometry integrating. Still 6.1 though. Maybe since this is, y'all are gearing up for a Unit 6 and 7 test, I might give this a little aspect of Unit 7 as well. So I'm going to start at 5, I'm going to go over for 2, then I'm going to go back down to 0 by 4. That's supposed to be a straight line. And then maybe over here at 10, we've got the rest of our half circle, which that looks pretty decent. Okay, so that would mean that this height would need to be 3 at that point. And I think that would happen at 7. Okay, and suppose this is a graph of f of x. Okay, and suppose also this, they said that the function g of x equals the integral from 0 to x of f of t dt. And we could find a couple of these values. I think I'm going to do 3 of them. I think I'm going to do g of 2. That's equal to the integral from 0 to 2 of f of t dt, f of x dx, same thing. So the integral from 0 to 2 is going to be the area of this rectangle here. It was supposed to stop there at 2, so maybe it's kind of like that. And that'll be 5 height to width, and that's going to be 10. Okay, g of 4 is going to be the integral from 0 to 4 of f of t dt. And that's going to be, well, that'll be the 10 plus the area of this triangle, which has a width of 2 and a height of 5. So half of 10 is, you can tell, but even from my low quality drawing, you can tell that that's half. Okay, 15. All right. Then if I asked for g of 7, I'd be integrating from 0 to 7 on f of t dt. And if I went from 0 to 7, I would have, the 15 from this, area here, plus the area of this quarter circle. Okay, the area of the whole circle would be pi times radius squared. Radius is 3, so it would be 9 pi. If it's just a quarter of that, that would be a quarter of 9 pi. Okay. And if I'd asked for g of 10, I'd have, instead of adding 9 pi over 4 here, I'd have added 9 pi over 2. Okay, and that's kind of your geometry integration. All right, in 6.2, we learned fundamental theorem of calculus. All right, so we just need to do just a couple of integrals. All right, so I don't know. I don't want to take too much of a risk. So minus 3, we'll say. Okay, and then maybe I'll do one with some trig in it. Maybe integral from pi over 3 to 5 pi over 6 of sine of 2 theta d theta. Okay, this is not solution, but it's not exactly, a straightforward antiderivative either. All right, so 12x squared, to take the antiderivative of this thing, which is the first step, I need to take the antiderivative, add 1 to the power, divide by the new power. And really, this is x to the 0, so we could add 1 to the power and divide by the new power, or we could just say that, okay, something whose derivative is negative 3 is going to be negative 3x. We're going to let that run from x equals 1 to x equals 2. And that would be, okay, 4x to the third is going to be 4 times 2 to the third is 8. Okay, minus 3 times 2 is 6. Minus, okay, when I plug in 1, I'll get 4x to the third is 4 minus, minus 3 when I plug in 1 for x there. All right, so I've got 32 minus 6 is 26. Minus the 1 is going to be 25. And then for sine of 2 theta d theta, I'm going to need an antiderivative for that. So an antiderivative for sine would be negative cosine. Leave the inside the same. But I know I'm going to need to divide by that 2 for the chain rule. And that would be as theta runs from pi over 3 to theta is 5 pi over 6. I'm not going to need to change my bounds of integration or anything because I didn't change into u's. So I'm going to say, and maybe I'll factor out that negative 1/2. Just kind of out of room here. Times the cosine of 2 times 5 pi over 6 is 5 pi over 3. Cosine of 5 pi over 3, you may have forgotten about 5 pi over 3, but that's going to be this one all the way down here. Pardon me, you can't even see that. Cosine here is going to be adjacent over hypotenuse. That's going to be 1/2. And then the cosine of 2 pi over 3, well, 2 pi over 3 is up here. And that's negative 1/2, and that's positive root 3 over 2. Right? And so I wanted cosine, and that's adjacent over hypotenuse, so minus negative 1/2, and that would be the value of that integral. Okay, that's 6.2. Just taking integrals. In 6.3, we did U-substitution. And so that one, I'll just show you a couple that fit the pattern. Maybe the antiderivative of hold on a second. Sine of x divided by the cubed root of 2 plus cosine x. And, at this point, as far as integration strategies, and that's something we'll talk a whole lot more in the next semester. At this point, if you look at something and it looks pretty complicated and there's not anything you can do for it algebraically, it's got to be U-substitution. So, here we've got, what is the derivative of what? Well, the derivative of 2 plus cosine x is 0 minus sine x, which is not exactly sine x, but it's close enough that I can use a U-substitution. Okay? So I'll say let u equal 2 plus cosine x. Then du dx is negative sine x. So du is negative sine x dx. I have positive sine x dx, so maybe I'll multiply both sides by negative 1, so it matches up perfectly. And then I'm going to substitute x, that's u. divided by, wait, no, sine of x is not u. Oh, no. Pardon me. U is in the denominator inside a cubed root, so that's cubed root of u. Sine x dx is negative du, so maybe -1 du, like that. Okay. If at this point you still have x's in your integral, you have done it wrong. Okay, you are heading down the road to a wrong answer if you have x's and u's in your integral at the same time. In this class, this is a single variable calculus class. If you cannot eliminate all the x's, you have not done it right. Okay, I cannot emphasize that enough. And then this is going to be equal to negative u to the -1/3 power. But maybe I'll factor out the negative outside the integral with respect to u. So I'm going to add 1 to the power. -1/3 plus 3/3 is positive 2/3. And then I'm going to divide by the new power. And I'm going to add c, right? Because this is an antiderivative problem. So dividing by 2/3, that's not great. And so that's -3/2. I need to back substitute on u. U is 2 plus cosine x. And I'm taking u to the positive 2/3 power and adding c. And that's how I did that antiderivative. Okay? I'll do a definite integral that will require a u substitution, but that also comes with a table or something. Okay, yeah, now you can see that. X, f prime maybe, 0, 1, 3, I don't know. I won't need this much. 2, 5, 9. I don't know. 1, 3, 1. Who knows? All right. Here I've got myself a table. Something like the integral from. Oh, I know just the thing. The integral from 0 to 3 of, say, f of x squared times f prime of x, getting off my shot, dx. Right? This is one, and if you wanted more like this that was table and u to u, you should go look at the extra practice for homework 6.2. That's where that practice is, and I've got a bunch of those there. So what I'm going to do is I'm going to say, what is the derivative of what? What could I take the derivative of to see something else in the integrand? I could take the derivative of f, and I would get f prime, and that is right there with multiplication in the integrand. So I say u equals f of x. Du is going to equal f prime of x dx, and I need to also convert the balance because it's a definite integral. That is going to be, what is it going to be? When x equals 0, u equals f of 0, which is equal to 2. And then when x equals 3, u equals f of 3, which is equal to 9 right there. So now I'm going to have the integral from 2 to 9 of f of x is u squared du. And now all of a sudden this became much easier. Okay, I can do that. Find an antiderivative. 1/3 u to the third. Let u run from 2 up to 9. And that's going to be 1/3 of 9 to the third minus 1/3 of 2 to the third. I know 2 to the third. I don't know 9 to the third, so I'm just leave it like that. Okay? And that's about as good as we can do. Okay, that was u substitution. Then the last thing I got, 6-4, some motion problems. I'm not going to do a whole lot of these because it seems like y'all were pretty solid on these, and we've done this a few times this year. But I will show you how to, compute some of these things. Suppose the velocity of an object is given by, I think I already, what was the last thing I did? Oh, that was in a different video. Maybe the 4th root of, what was it? T to the 6 plus 2. But I actually probably want something that's going to go, actually, I don't really care. That this is always going to be, maybe I could subtract 10 or something so that it would be negative sometimes. Okay. Yeah, that's what we'll do. And if I want, say, suppose the position of the object at time 0 is equal to 8. Yeah, I could ask you about a displacement type situation. I could ask you about the position of the object at time 5. and I could ask you about the total distance on the time interval 0 to 5. And that would, yeah, similar integrals, but slightly different. Okay, so for x of 5, we know that x of 5 equals x of 0 plus the integral from 0 to 5 of the derivative of x's velocity. Just write v of t. It's kind of a lot to type. And then that's something I can use a calculator for. But I know since I'm going to need to use this function twice, I don't want to have to type it twice. So I'm going to type in the fourth root, which we can do like that. Put the fourth root in. But maybe you don't have that option on your calculator. And if that's the case, what you're going to do is you're going to use parentheses, t to the 6 plus 2 to the 1/4 power, and then subtract 10. And that's in y1. So if I want to do x of 0 is 8 plus the integral I get by pressing math and 9 from 0 to 5 of v of t I programmed into y1, I can get that by hitting F4. So I go to F4 and choose y1 with respect to the x. It's going to think for a second. I get negative 18.712. Pardon me. And then for the total distance traveled, I need to set up an integral for that one. That will be the integral from 0 to 5 of the absolute value of v of t. And that will be equal to, I can't compute that by hand. I need to go over here. And I'm going to integrate math 9 from 0 to 5 of absolute value I get by pressing math and scrolling to the right by 1. It's also an F2 if your calculator has those nice F menus. And then I'm going to call on y1 and integrate with respect to x. That might take a little longer. It's got to take the absolute value and then throw it into its massive Riemann sum that it's computing right now to approximate our area. There you go, 27.134. Okay, and that's almost all I've got for you, but not all. I've got a little more. Okay, I forgot to tell you about the average value of a function. But, you know, if you've watched this far, then, you know, maybe you deserve to see that little extra bit. So the average value is, remember the definition of average value is the average value of f on an interval, you know, a to b is equal to the integral from a to b of f of x dx divided by b minus a. Okay? So maybe, for example, I will work a average value of let's just say sine x on the interval 0 to pi over 2. That might be interesting, right? Because you know what that looks like. 0 to pi over 2, that's just that part of the graph of sine x. And so what we're going to do is 1 over pi over 2 minus 0, integral from 0 to pi over 2 of sine x dx. And that would be, antiderivative would be negative cosine x as x runs from 0 to pi over 2. Oh, whoa, forgot to divide. So it'll end up being 2 over pi, I'm off my screen, times, because 1 over pi over 2 is 2 over pi. And maybe I'll factor out the, no, I don't think I will. Because negative cosine of pi over 2 is going to be 0, because that's the x coordinate. Okay, so negative 0 minus negative cosine of 0 is 1. So this is just positive 1, and that's equal to 2 divided by pi. That makes sense because pi is bigger than 3, so this average value would definitely be less than 1 because I know that the maximum value here is 1. But, you know, it's bigger than half because it does a lot of its growth early. You know, I'll let you think about what that means. All right, I think that's going to be all. Yeah, I'm pretty sure I have hit just about everything that I need from Unit 6. Thanks for watching.